A titration is a common laboratory method used to quantitatively determine the concentration of an unknown solution. The purpose of the titration is to quantitatively determine the concentration of an unknown solution. There are many real-world applications for titration, such as finding the blood glucose levels in patients with diabetes, in the food industry to find vitamin C concentrations, or by pharmacists to achieve a desired mix of compound drugs. First, you will start off by putting your titrant into the burette. As you are putting it in, you will open the stopcock to let out the titrant. This will condition the burette. Conditioning 2 to 3 times will ensure that the concentration of the titrant is not changed by any water or anything else that was in it before. Then you will fill the burette up with titrant until the meniscus is at exactly 0. After this, you will add your analyte into an Erlenmeyer flask. Add 3 to 5 drops of your solution. Then swirl it around a bit so that everything gets mixed up well. First, you will do a fast trial, which is the opening of the stop clock until all the way so the titrant pours into the analyte until you notice the color change. It is okay if you overshoot because the purpose of the fast trial is to get an approximation of the amount of titrant you need to reach equivalent. After the fast trial, you will rinse out the flask and add the same amount of analyte as before. Next, you will open the stopcock a few mLs before your approximation. So suppose your approximation was 10 mLs. So then you can stop at 9, 8, or 7. Then go close it until only drops fall into the solution. So this will help you get the exact number of like the exact amount of titrant that will go into the solution without overshooting. So as I was saying, when you get to this point, you will close the stopcock enough so that drops will fall slowly and to let the titrant into the solution. As you are letting the titrant into the solution, you will swirl and observe the color change. When the analyte solution completely reaches the desired color change, that is when you need to stop the stopcock from adding more titrant. You have to do this fast. Then your titration is done. You will take the difference in volume to determine how much titrant was used and neutralize this analyte. Then you will do the calculations to find the concentration of the analyte. Accurately define analyte, titrant, indicator, endpoint, and equivalence point. So analyte is the solution of unknown concentration. Titrant is the solution of known concentration. Endpoint is the slow point at which enough titrant has been added with all the analyte without any leftover reagents. Visually, with the indicator, there is a color change. So, for example, sodium hydroxide reacting with sulfuric acid with an indicator will turn light pink. An equivalence point at which the amount of titrant is added just enough to completely neutralize the analyte solution. So for example, these numbers aren't accurate, but this is just an example. So using 10 mLs of sodium hydroxide to neutralize 20 mLs of sulfuric acid. So the endpoint and the equivalence point should ideally be happening at the same time, but when they don't, that is when there is error. Accurately describe a typical setup for a titration, including appropriate glassware. So first, you have to clean all your glassware. You never know what was in it before. Then you make the titrant solution and the analyte solution. Then you have to condition the solution, condition the burette. Conditioning 2 to 3 times will ensure that the concentration of the titrant is not changed by any water. So conditioning is just putting the titrant into this burette over here, and then letting it drip out into the Erlenmeyer flask down here. So basically, when you're doing a titration, in the burette, this is where there's titrant, and the Erlenmeyer flask down here is where there is analyte. And this is the stopcock. When it's straight like this, when that line and it lines up with the burette, that means it is open, and that means water will the titrant will come in and at full speed, and as you like make it horizontal, it'll slow down until it is fully horizontal and it'll stop. Accurately describe the purpose of standardization of the titrant. Standardization is used to determine the exact concentration of the titrant. It is usually achieved by titrating the solution to be standardized with a known amount of primary standard substance. We do this because the titrant might be unstable or hygroscopic, which means it absorbs moisture from the air. Characteristics of a primary substance are that it is high in purity, it is stable, has a high molecular mass, it is non-hygroscopic, which means unable to absorb moisture from the air. So the reason these qualities matter is because high purity is that so that the mass truly represents the moles of the substance present. It is stable because we don't want it to be reactive with anything else. The high molecular mass is to minimize massing errors, and non-hygroscopic is so that to minimize mass charges due to humidity. An example of standard substance is KHP because it is stable, high in purity, non-hygroscopic, and highly soluble. Accurately describe how the endpoint and equivalence point is determined. The endpoint is the slow point at which enough titrant has been added with all the analyte without leftover reagents, visually with the indicator, a light color change that doesn't go back to its original color. The endpoint is determined when you reach your desired color change. The color depends on the indicator, titrant, and analyte. For example, the endpoint for KHP, which is the indicator, sodium hydroxide, which is the titrant, and sulfuric acid, which is the analyte, is light pink, while the endpoint for black tea indicator, which is the indicator, EDTA, which is the titrant, and calcium chloride, which is the analyte, went from red to purple to blue. So it's different for a lot of indicators and analytes and titrants. An equivalence point is found by finding the amount of titrant it took to neutralize the analyte. For example, these numbers aren't accurate, but it's just an example. So if it took 10 mils of sodium hydroxide to neutralize 20 mils of sulfuric acid. So that's the equivalence point, the amount of titrant it took to get to that, to neutralize. So ideally, the endpoint and the equivalence point should occur at the same time, but when it doesn't happen, that means there's some error that happened. Accurately describe how to determine the unknown concentration of the analyte from raw titration measurements. So the equation is average concentration of titrant times the volume of titrant dispensed times the mole to mole ratio times the 1 over the amount of titrant used in liters equals moles of analyte over liters, which is also molarity of analyte. For example, in a titration as NaOH as the titrant and a 0.2 liters of sulfuric acid solution as the analyte, the concentration of the titrant is 2.859 times 10 to the negative 9 molarity. 0.0084 liters of titrant was used to reach equivalence, and the mole-to-mole ratio of the sodium hydroxide and sulfuric acid is 1 mole of sulfuric acid to 2 moles of sodium hydroxide. Now that we have all we need, we can just plug in everything into the equation. So we have 5.872 times 10 to the negative 6 moles of sodium hydroxide over 1 liter times 0.0084 liters over 1 times 1 mole of sulfuric acid over 2 moles of sodium hydroxide times 1 over 0.2 liters, which all comes out to 1.233 times 10 to the negative 6 moles of liter of the sulfuric acid, which is saying that the molarity of sulfuric acid is 1.233 times 10 to the negative 6 moles. So this is the practical. So I start off by putting the titrant into the beaker here, just so it's easier to pour. And I'm actually conditioning the beer right now. You can see that it is all dripping down. I'm not keeping any of it, and it's all dripping down, so that basically there's nothing that affects the concentration of the titrant in here. Yeah, this takes a while to happen, but this is what happens. And then I stop it, and now I'm pouring the titrant so that it goes all the way, so that the meniscus is at 0. As yeah, you can see me pouring it into the beaker. All right. I'm not exactly the tallest person, so I have to really look up to see what's going on. And I'm just letting a bit of titrant out because I over poured a little bit, so I have to get it down to exactly 0. So there's a picture of the titrant. You can see that it is at exactly 0. The meniscus dips down to 0. So now we're starting the titration. So my solution, my analyte is already in here, and this is the titrant in here, in the burette. As you can see, as I'm pouring it, it's starting to turn pink. And since I did a fast trial before, I got it down to like 10, so that I stopped a few mLs before, and I'm gonna stop a few mLs before I get to 10, and then just do only drips. And as you can see, when it was really pink before, but when I shake it up, it goes back to clear immediately. And I'll just keep shaking. So you can see that I'm doing it just so that just drops come. And I'm just shaking it. I keep noticing the color change. I'm just doing it until I see the color change. And you can see that when I keep adding it, it's taking longer to go back to clear, which means that we're getting closer to the end point. See? And now, see, it's a light pink. So this means this is the desired color change that I was going for. And now this just means that I got the exact amount of titrant that I needed. And I got all the way down to 9. I got all the way down to 9.1. So that's my mastery for titration. Thank you.